which is fine, but I will have to ponder the questions which have been asked. I can usually answer math questions more quickly. It's questions of scheduling and planning that always take me longer to figure out. Anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless our time and help us to understand a little bit more about the Fourier Transform and how all these things work together, Lord. In your name, I pray, Lord Jesus. Amen. So, I feel like I have done a passable job explaining what the Sturm-Liouville system is and how it kind of defines a whole world of solutions, and that solutions has its own geometry and notions of completeness and all kinds of other things. It's really neat. And connected to this discussion is the larger discussion of Fourier analysis, and before even that, as I talked about at the end of last time, inverse differential operators and Green's functions. So I'll be real brief about section 5.10. I want to make sure we have written these things out just briefly, if nothing else. So LU equals to F is a typical boundary value problem for an ordinary differential equation. Can be written in operator form as LU equals to F. So what do? We seek a solution U that satisfies this equation and a given boundary conditions, right? And then typically where U is going to be an element of some particularly appropriate set of functions. So he talks about the domain of the operator DL. So it's the space of functions satisfying whatever boundary condition you're interested in, all right? And he says one way we would approach the problem is by looking for the inverse operator L inverse. If it's possible to find inverse, then the solution can be obtained by, well, L inverse of LU would then be equal to L inverse of F, and so your solution then would be U as L inverse of F. Of course, you know that this is some kind of a lie because first of all, inverse is good for pre-calculus, right? We can talk about invertibility of a function if it's injective, right? But we know that typically these functions, this operator is not injective. Like if you put LU equal to 0, that's the homogeneous problem, and there's typically an infinity of solutions to that. So it's far from one-to-one. And but setting aside that, you can look for an equivalence class of solutions, right? Maybe think of this as giving you the particular solution, and then you can add the homogeneous part to that, and then you get the whole solution, right? Something like that. And so in particular, the Green's function, what is Green's function? Well, Green's function is some function that you can write the solution like this. U equals to L inverse F at X. And you can write that as integral from A to B of, and so I say integral from A to B here, but in practice, in different contexts, that might be, a different kind of integral. Maybe it's, well, first of all, not from A to B. Maybe it's like an infinite integral. I don't know. I don't think this is written in stone, okay? But certainly that's the kind of integral you'd expect for like the Sturm-Liouville problem on the closed interval from A to B, all right? And so he has some discussion about what Green's function looks like in terms of the Sturm-Liouville problem. He actually writes a formula for it in terms of the homogeneous solutions and the Wronskian. And then he talks about how you can derive a formula for the particular solution by the method of variation of parameters. It's pretty standard stuff there. That actually generalizes for nth order problem, but it comes at the cost of dealing with matrix calculation. In any event, then he has a theorem, which is that the operator T defined by 5.85 is a self-adjoint compact operator. So he for the Green's function that comes from the integral operator that is born of the Sturm-Liouville problem, you get a self-adjoint compact operator. All right, anyway, great. Woohoo! Audric is back. I haven't even defined the Fourier transform yet. Audric, we're still in the Green's function preamble.
Okay. Oh, good. I was like, oh, we're doing Fourier. I just barely started that.
So, it says theorem 5.10.3, lambda equals 0 is not an eigenvalue of the Sturm-Liouville system. And I'm saying Liouville wrong, by the way. Dr. Scambortis said it, and it sounded beautiful. I'm saying it wrong. I should have called Dr. Scambortis in here to say the word. Oh well, it's too late.
It's a long theorem, so after, can you move me? Because I already have the state written down.
I will not move you. That's where you're going to be. That's your home. Get used to your home. I'm done moving you. I'm fine. I'll move you. I don't think you're missing anything much. Oh yeah, you're kind of tilted, aren't you? Let's see.
Yeah. No, this is a long theorem, so.
And then, so lambda equals 0, not an eigenvalue of the Sturm-Liouville system defined in theorem 5.10.1. Then lambda equals 0 is not an eigenvalue of the integral operator t defined. Okay, so the integral operator t, I don't really have much to say about this. I don't know. I probably even shouldn't write this down, guys, because I really have no intention to really do much more here on this. I'm just trying to do enough here that the next section is plausible. All right. But anyway, if you define t of f like that, and I mean, so it seems to me like it's the inverse operator for L, right? Theorem 5.10.2 says it's a self-adjoint compact operator from Lebesgue integrable functions L to AB into continuous functions A to B. And it says also, then the next theorem says if lambda equals 0 is not an eigenvalue of the Sturm-Liouville system in the sense we defined last class, then this operator T will not have 0 as an eigenvalue. And then theorem 4 in this section says under the assumptions, lambda is an eigenvalue of L if and only if 1 over lambda is an eigenvalue of T. Aha. So L of U equals lambda U only if, let's say, TV is equal to 1 over lambda V for some V. In other words, if lambda is an eigenvalue for L, 1 over lambda is an eigenvalue for this T. This is nothing particularly surprising. This is the same story we see in finite dimensional linear algebra. If you have an invertible matrix and 2 is an eigenvalue for A, then 1/2 is an eigenvalue for A inverse. This is always, this is also true in finite dimensions. Nothing much to see here, okay, guys? All right, so now that we're all here, let's get started on section 5.11. Actually, let me erase all this, Audric, because, it doesn't matter too much. I think. Oh, that isn't going to go past what I'm about to do? Oh. Well, I really do want to talk about the Fourier transform, though. It's interesting. And I don't think, man, if there's anything that gets gets shortchanged in the standard math curriculum, I would say it's the Fourier transform. Because it's hugely important to engineering. And also, the Fourier transform has abstract versions. Yes, there's the one we do in science and engineering, but there is an abstraction of the Fourier transform that is currently a research topic. I mean, it's not something that's dead. It's an active,
I like the
topic.
engineers when they talk about dating, because they say people send them mixed signals, so they do a Fourier analysis.
That's horrible. Yeah. All right. So here we go. So we're going to try to describe the Fourier transform here. We're section 5.11. All right. Let's see here. So here's the definition. This is the Fourier transform in L1R. Let f be an element of L1R. What did that mean? Yeah. That was the Lebesgue integrable, right?
Yeah.
Then f hat of omega is equal to 1 over the square root of 2 pi integral from minus infinity to infinity e to the minus I omega x f of x dx. This is called the Fourier transform of f. What's going on, Audric?
Nothing much. My roommate broke something.
Oh, I thought you seemed distracted. Well, hopefully nothing too.
They had a remark here that all functions in L2 is not integrable. Is that true?
Let's see here.
I didn't do this exercise, but in chapter 3 exercises, this is L2 is the only inner product space out of the LP spaces, I believe. Where is it? Problem 14, page 136. L2 of AB is the only inner product space among the spaces LP of AB. And the L2 inner product is just the integral of function times function conjugate.
So he's playing some kind of funny business here, where he's defining an L1 and then extending it.
Yeah, he's intersecting it. But like, what function is that? I thought like that was the whole point of the L2 space, was to get like things that are normally not integrable under Riemann to get under integrable.
Yeah, well,
well, maybe he's talking about like null functions, I guess. But don't null functions exist in L1 too?
yeah, you can still iterate functions across. I'm sorry, where were you reading again when you said? Oh, you said something there.
250. He's reading 258. He's like, this cannot be used. The integral cannot be used as the definition of the Fourier transform in L2R, because not all functions in L2R are integrable. However, however, it is possible to extend the Fourier transform into the intersection of L1 and L2R onto L2R. In the first part of this section, we discuss properties of the Fourier transform in L1. Then we show that the extension onto L2 is possible and study properties of that extension. So.
Yeah, sorry, I was thinking something different.
So Audric, you're asking.
Like, yeah, what functions? Like, have we just been kind of like hand waved, like hey, this.
Well, what is L2R?
It's the integral functions that had that norm, that had the.
All right.
It's integral of absolute value.
Where is that?
It should be in 2.13, the LP spaces. That's the norm.
All right. So yeah, definition 2.13.1 on page 74. By LPR, we denote the space of all complex-valued locally integrable functions, such that the p power of them is in L1R. So to say that not all functions in L2R are integrable, what would that mean?
I feel like we've answered this question before. I just can't remember, or like they've mentioned this before. I just don't remember like quite punchline.
Well, I guess if it's not, then you can't find a sequence of step functions such that all those conditions of the big interval or
Yeah.
that or something.
Mhm. Not all functions in L2R are integrable.
I mean, they're just examples. I mean,
Now, how is integrable defined?
it's defined the usual way, you know, just that we say something is Lebesgue integrable if there's a sum of there's a sequence of
It's
functions and that.
It's L1, right? Basically.
Yeah.
That's
You just extend
page
it.
I mean, it doesn't involve any squaring, does it? It's just, what page, what is it?
Page 45 is the L1. Yeah.
Page 45. Let's see here. Right, so L2, all right, let's see here. Oh, goodness gracious. I want to say,
Yeah, it is, yeah, the absolute value back to the P is in L1. So, yeah,
You
it's
take the absolute value, you square it, and then you take it by 1/2, like you just.
Yeah.
so I think, for example, f of x equals 1 over x. If you integrate 1 over x, absolute value, over the real line, it diverges. But if you square it, it's 1 over x squared, and that converges.
Okay.
So it's, the reciprocal function, I think, would be an example of a function which is L2, but not L1.
That makes sense.
Although, that's not quite the right example either, because you've got the divergence at 0, which I don't want, so you could.
Well,
We can move on. It's just like
page 80. I didn't do
Page-
this problem, but page 88.
Page 88?
Homework problem 32. So that the function, I think this is called the Dirichlet integral, if I'm right, is not Lebesgue integrable. I mean, so there's an example. I mean, that's just in L1. So I mean, if we have a function that's not integral in L1, I guess it would make sense to have functions not integral in L2.
No. There's counter examples to that. Like there's stuff integrable in L2 that's not in L1, and L1 that's not in L2.
That would make sense. I was pointing out.
Yeah.
L1 that's not integral.
That's interesting. So we did have the theorem that if a function is integrable in the proper Riemann sense, then it's Lebesgue integrable, right? But the converse wasn't true, right? Lebesgue integration is more general than Riemann integration. But this is interesting, that problem 32 on page 88, that's an example of a function which is not Lebesgue integrable, but the improper Riemann integral converges. So
isn't that the topologist sine function?
that is.
Pretty sure that's what that is. I did this problem. I gotta go find it somewhere.
I think it's the derivative of the Fresnel function. Fresnel function. It comes up in optics, but
yeah.
Okay, let me get back. So this is the Fourier transform. All right, and so let's see here. Let's work out an example. Example 1. Suppose you want to, and we have notation. This is also like funny looking f. Well, I'll just do it like this. F of, what's his notation? Curly brackets, f of x. And you might write of omega here. I don't know how explicit you want your notation to be, but that was supposed to be an omega. All right, so let's calculate it. the Fourier transform of e to the minus alpha absolute value of x, all right, is equal to 1 over the square root of 2 pi, integral from minus infinity to infinity, e to the minus I omega x, e to the minus alpha absolute value of x, dx, which he rewrites as 1 over the square root of 2 pi, integral from minus infinity to 0, of e to the x times alpha minus I omega, dx plus 1 over 2 pi, integral from 0 to infinity, of e to the minus x alpha plus I omega, dx. All right, so these integrals are pretty easy to do. Integrating with respect to x, we just get what? Like, yeah, we get 1 over alpha minus I omega, right? E to the x times alpha minus I omega. That's this integral. And I'm going to write it, evaluate from minus infinity to 0. Plus 1 over root 2 pi, 1 over alpha plus I omega, e to the, and there's a minus here, right? Minus x times alpha plus I omega. Evaluate that thing from 0 to infinity. And of course, don't tell my calculus 2 students about this. I'll deny it. But if you plug in minus infinity into this, that goes to 0. Technically speaking, you have to make a squeeze theorem argument because it's a sine and a cosine, but the kind of sine and cosine are modulated by an exponential with a negative argument, which is becoming arbitrarily large and negative, and as such it squashes the bounded sine and cosine that are implicit within this I omega term here. Similar story over here, the infinity term dies out because you're looking at something of modulus e to the minus x alpha, which goes to 0 as x goes to infinity. And so we just get the zeros. So we get 1 over root 2 pi, 1 over alpha minus I omega, and then over here plus 1 over alpha plus I omega. And then make a common denominator. You got yourself alpha plus I omega plus alpha minus I omega divided by alpha squared plus omega squared, because those are conjugate. And they multiply out like that. And what you got, your omegas be canceling. And lo and behold, we've got ourselves a 2 alpha over the square root of 2 pi alpha squared plus omega squared. So yeah. Example 2, calculate the Fourier transform of e to the, what's the next example he's got here? E to the minus alpha x squared. So now we're looking at 1 over 2 pi, root 2 pi, integral from minus infinity to infinity. And we've got what? E to the minus I omega x, e to the minus alpha x squared dx. And it can't be too hard because he does it in like 2 lines here.
Oh, he's
Whoa.
Is he using the formula for the Gaussian?
No,
Whoa.
that's not that bad. You just gotta square it. Like, if you squared out the terms, the stuff will start canceling out. Until you're left with, like, omega squared over t, over, like, 4 alpha. You just gotta square it out.
Mm-hmm. Yeah.
All right, so, yeah. So 1 over root 2 pi, integral from minus infinity to infinity of exponential. And we'll factor out the alpha, I think. And then that gives us x squared plus omega x over alpha. I lost my I, that's not good. Then complete the square on that. So you've got x plus I omega over 2 alpha, quantity squared. And then let me put some big old parentheses in here, minus I omega over 2 alpha, quantity squared, dx. But this gives you a I squared is minus 1, that minus minus becomes a plus, but then this is a minus, so you get a net of 1 over root 2 pi e to the minus omega squared over 4 alpha squared, no, 4 alpha, because that alpha and this alpha squared reduced to give me just an alpha. And then you've got the integral from minus infinity to infinity of the exponential of minus alpha times parentheses, x plus I omega over 2 alpha, quantity squared, dx. But that's a Gaussian integral, right? That's the Gaussian integral. And so that you can look up, or I mean, you can calculate if I have another 20 minutes, well, 10 minutes, but anyway, what's that integrate to? That integrates to, what'd I do? So
It's 1 square root alpha times.
yeah, this is,
1 square root pi alpha.
so he makes this minus alpha u squared, right? Like that. And if this is u, right? Then dx is equal to, if this is all du, oh, dx is du, isn't it? Because it's shifted, it's not multiplied, so that's dx is du. Okay, great. And what was the integral of the Gaussian?
I think it's square root of pi over
Square root of pi over alpha.
alpha, sorry, yeah, I think so.
Yeah, I think there may be a.
That would make sense because he's canceling out the pi and it's going to.
Okay, so that cancels, and so you get you get e to the minus omega squared over 4 alpha divided by square root of 2. The pi is be canceling, but the alpha remains. I think that's what he had. Yeah, there it is. So this is pretty cool because if you have a differential equation which involves the Gaussian, the Fourier, I mean the Gaussian is a notorious thing, but this shows that the Gaussian actually has a relatively tame Fourier transform. And actually it's kind of interesting because it answers a question you might ask. The Fourier transform of what function has the same form after the transformation? Answer? Gaussian. See, same, go from exponential. It's still a Gaussian, but in the frequency domain. Now we could also play other games like what's the Fourier transform of cosine? Or how about this? What's the Fourier transform of e to the, ix?
Yeah.
Or not ix, let's be more interesting, I beta x, where beta is a constant. So basically, what am I doing? I'm putting, and you can throw an absolute value in there if you want, just to make sure I don't have to worry about anything. So I'm just putting alpha, right? I'm putting minus alpha equal to I beta. So this just becomes what? 2
I beta.
minus 2 I beta.
Minus beta. Oh, sorry. Over the square root of 2 pi
Yeah.
times quantity.
Square root 2 pi.
Beta.
Alpha squared is, so omega squared minus beta squared?
Yeah. Yeah.
Something like that. I wonder if that's right. I mean, I just did this. I'm not saying it. I mean, I just did this. I mean, I could be wrong.
Yeah, you're just plugging something in for alpha. Right?
Yeah.
So the same.
Oh, okay. So yeah, let me. I have to be careful of the time, Audric, because I got church tonight, and I can't go on too long here, and I do want to try to get to some things besides just defining the transform, right? So, okay, going on here. So theorem 5.11.3, the Fourier transform is linear. So like alpha f plus beta g is equal to alpha times the Fourier transform of f plus beta times the Fourier transform of g. All right. And we also have a theorem that the Fourier transform of an integrable function is a continuous function. All right, that's nice. He has his theorem 5.11.5 says that if you have a sequence of functions that are in L1R and they limit to f, let's say, then the Fourier transform of the sequence limits to the Fourier transform of f. Let me just write that out. Yeah, so if fn goes to f, then fn hat goes to f hat. And this is uniformly so. Whereas this over here is not a uniform limit, it's just a, oh, I'm sorry, Audric, I seem to have left you on the other table. My bad. Oops. Ah. Sorry.
Yeah.
I was making community jokes in physics today because they were talking about physics. They were talking about community, and so I was talking about magnitude, and I just followed it with pop pop, and they didn't get it, and I had to explain it. And I was like, fine. All right. All right. So let me skip past. I'm not trying to give you all the technical, niceties here. I'm really just trying to focus on the big points. And so this theorem 5.11.7 these are the big ones. So if you have the Fourier transform of e to the I alpha x times the function of x, that is going to give you f, the Fourier transform of omega minus alpha. All right. And if you remember your Laplace transforms from differential equations, these are actually kind of interesting because you can make an analogy here that the imaginary exponential is to the Fourier transform as the real exponential is to the Laplace transform. So there's similarities. Oh, he doesn't write omega. I'm going to write omega though. Well, that was interesting. Yeah. Some kind of thud in here, Audric. I don't know what's going on. Minus omega, minus I omega x naught. Fourier transform of f of alpha x is, well, that's interesting, 1 over alpha f hat of omega over alpha for alpha greater than 0. And how's it go? How's conjugation go here? Well, the Fourier transform of the conjugate of f is in fact equal to the conjugate of the transform. Oh, but not that. The conjugate of the transform of f of minus x. Interesting. So then I think he uses these properties to calculate the Fourier transform of the modified Gaussian. Let's see here. All right. So these, if you're actually doing calculations in Fourier transforms, these are important to understand the mechanics of it, all right? But what's even more important is the one I'm about to write. So if you learn nothing else about Fourier transforms, understanding the theorem I'm about to write is of utmost importance. It's really the signature move for the Fourier transform, the next theorem. And I think we can derive it, I think. So here it is. And I'm throwing domain issues to the wind, okay guys? So I understand there's nuanced things to say about once or twice Lebesgue integrable, and for shame that I'm not talking about them in this course, right? But I will not let perfect be the enemy of good. So let's go on here. So it's simply this: the Fourier transform of df dx, all right, is equal to I omega times the Fourier transform of f.
Oh, it's like that. Is this in momentum space kind of?
Yeah. I need to transform you again. Shift. Here's a shift operator for you, Audric. Is that better? Are you?
Yes. Okay.
Think you can see. Yeah. All right, so let's see if we can derive this. I'm going to take a breath, work this out. So if we're calculating the Fourier transform, so if you guys get a chance to teach differential equations in grad school, it's really a nice thing to teach, because one of the really cool things about differential equations is when you get to Laplace transforms, you discover, if you try to work out the theorems for yourself, that you can. If you're just a little bit nonchalant about the analysis, the proofs are really just calculus 2 for the most part. They're integration by parts, and stuff like that, actually. And I would wager something similar will happen here. So let's see here. If I what if I do d dx of e to the minus I omega x times f? What's that give me? Minus I omega e to the minus I omega x f plus e to the minus I omega x df dx, right? So I have this to start with, right? And I can trade it for, so, you know, what I'm doing is integration by parts, but I like to actually, when I'm doing these kinds of abstract things, I like to actually write out the product rule and think about it just to make sure I'm not deceiving myself, you know? So apparently, there is some kind of license given to us to assume that this, because the integral of a total derivative, right? So as you carry out that integration, what happens is you end up evaluating the thing you're finding the total derivative of at the endpoints, right? So like, I can think of this piece basically going to e to the minus I omega x f evaluated from minus infinity to infinity. What? There must be a reason that we know that that dies out. I think that would be based on the preconditions that I glossed over. You know, the Lebesgue integrability of the function and the assumption that its derivative exists, stuff like that. So that must vanish. I think it makes sense that that vanishes if you think about it. If it didn't vanish, if f blew up, right? If f was unbounded as x went to minus or plus infinity, then it wouldn't fit the bill. It would not be able to meet the conditions of this theorem, namely that f and f prime are in L1R. And also, it explicitly says there the limit as the absolute value of x goes to infinity of f of x equals to 0. So there it is. I mean, this goes to 0.
Part of the hypothesis, yeah.
Yeah, so essentially it's built into the theorem, right? This goes to 0 at these two, at both of those extremes.
Yeah, the f goes to 0.
So then one more step. This is equal to, I omega times 1 over the square root of 2 pi integral minus infinity to infinity of, where were we? Golly. My bad. Oh, f. Duh. Sorry. But that's exactly the Fourier transform of f. So there you go. I omega Fourier transform of f. And that's the theorem. So if you can do it once, you can do it again, right? So like the next theorem after this is if you have the Fourier transform of, f prime prime, you get I omega squared Fourier transform of f. But to put it into words, the Fourier transform turns differentiation into multiplication by I omega, right? And the Laplace transform also does this. The Laplace transform also has the property of transforming a derivative in the time domain to multiplication of s in the frequency domain. And there's also a plus minusness to the derivative rule. But anyway, now then we have a convolution theorem. If you have the Fourier transform of the convolution of f and g, it is the product of the Fourier transforms of f and g. You could look at that in terms of, algebra. That's like a homomorphism property, right? Multiplication in the sense of convolution is becoming multiplication in the sense of, functions of omega. Yeah. And let's see here. He then gives the, the extended definition of the Fourier transform, which I don't really care too much about today. Essentially pointing out that if you have a sequence of functions with compact support that converge to L, then the Fourier transform is defined to be the limit of the sequence of the functions. So basically you extend the Fourier transform by using limits of appropriate sequences of functions. It's kind of like that homework problem you guys are working on, extending the inner product to the completion of the space. It's somewhat akin to that.
I did do this stuff. Just did that.
What's that?
I did that problem. So
Theorem, I thought that problem looked neat. Theorem 5.11.14, known as Parseval's relation. What's it say? It says that the magnitude of f hat in the 2 norm is equal to the magnitude of f in the 2 norm. So, well, here's what he says. In physical problems, the without the hat is a measure of energy, whereas the one with the hat it represents the quote-unquote power spectrum of f. Oh, well, this is, well, theorem 15 I don't want to write down. Okay, fine, I will. Theorem 15 is actually interesting. You know how we talk about the integral from minus infinity to infinity needing to be need to be taken asymmetrically? You know, like we can have we can't just take one limit for limit minus infinity to infinity. We have to let the limit goes to infinity and limit goes to minus infinity approach separately. This is a place where that's not the case. See, because what this theorem says is that f hat omega is actually equal to the limit as n goes to infinity. Notice that 1n goes to infinity of 1 over the square root of 2 pi integral from minus n to n of e to the minus I omega x f of x dx. So if you look at what I just wrote, you notice, I mean, that's essentially an improper integral, but it's an improper integral calculated improperly in the sense that we're approaching the limit symmetrically, right? So there are, indeed, there are functions, right, for which the improper integral diverges, and yet this converges. In fact, I think this takes us back to my original example, give or take, because the, you know, like, what, do you guys know what this is called? We talk about this briefly in complex analysis. You may or may not remember, Audric. This is the principal value. The principal value of the integral is when you take it symmetrically. So like the, so it's principal value. And there's lots of functions that the improper integral blows up, and yet the principal value is finite and can be calculated, and indeed is quite amenable to techniques of complex analysis. So I guess that's the other reason that Fourier transforms get shortchanged in the undergraduate curriculum, is there's a relatively small portion of the audience which actually has a mastery of complex analysis in the sense of computational complex analysis. And you do need computational complex analysis to do these things, because the calculation of these kinds of integrals immediately begs questions of like contour integration in terms of actual practice here. All right, so moving ahead, there is a there we go. I'm trying to see past his lemmas and I want to get to the big theorems, right? I'm trying to not write on the board the intermediate theorems, if that makes sense to you guys. So I think corollary 19 is really corollary 5.11.19 is the next big event here in my estimation. And what this says is that if f is an element of L1R intersect with L2R, all right, then f of x is equal to 1 over root 2 pi integral from minus infinity to infinity of e to the I omega x f hat of omega d omega. So do you see what's going on here? Right, so it's similar. It looks similar to the...
Is this the inverse Fourier?
Yep, that's the inverse Fourier. So what we're looking at here is the inverse Fourier transform of f hat. Yeah. Ooh. What? What? Surely that's a typo. His duality theorem is blowing my mind. He's got the Fourier transform of the Fourier transform of f on page 267. I do believe that that is a typo. Surely that's a typo. Because we can't take the Fourier transform of the Fourier transform. That wouldn't make sense. The Fourier transform is a function of omega.
Yeah.
So I think what he means there, since f of x is going in, indeed the Fourier transform of f of x makes sense, but I think what he wants is that the inverse Fourier transform of the Fourier transform of f of x, right, is equal to f of minus x. His proof is it suffices to replace x by minus x in the equation that I have written above. I don't know. Can you see that?
And we just have to work it out, you know? But I mean, it would just change it to e to the minus I omega x.
And then that f hat will be the Fourier transform of f of x. So replacing the f hat with all this stuff.
It's funky. I mean, it's a little bit unnerving to me. It's not a true inverse, is it? That's not quite right. So, all right, if I feed this, right, into the inverse transform, what happens? So this is my f hat, right? So I'm supposed to do what? 1 over square root of 2 pi. The omega, right? So we got a 1 over 2 pi out front. Whoa. Whoa.
Are we pulling the I omega x inside the interval? Like Rouvini's or something going on, and then we just get double interval of, oh no, wait, no.
I think I can tell you this right now. To quote my community college professor, this dog will not hunt. I believe we need ourselves a distinction. Let's call this at x bar. So the inverse transform at x bar. So that puts an x bar here. But it does not put an x bar here because this is the integration that defines the Fourier transform of f. This is a dummy variable of integration. And so in light of that, we get like, and then this is a constant with respect to that integration, so I can bring it in. And I have exponential of what? Exponential of like I. Do I? No, the omega. Now I'm worried about the omega as well. No, I'm okay. Well, stink. Is that the same omega? Yeah, that's the same omega. This omega and that omega, they're all tied. This is f. This is quote unquote f hat of omega. It gets paired with this I omega x hat. It's all the same omega. We're okay. All right. So I omega x bar minus x. Yeah. F of x dx d omega. Oh, there's math here I've forgotten about. I've done this. It's been a while since I've done this. I remember this from quantum field theory. Goodness gracious. He is hiding some stuff here. I mean, he may be being honest there. I mean, well, let me say it this way. If he's right, if it does suffice to replace x by minus x in that equation, and yet this is also something you can do, it says something profound about that integral. You know? As I recall, it gives you like a Dirac delta or something. But a 2 pi appears. Those 2 pi's, and those 2 pi's, like there's a Dirac delta that somehow appears, and that Dirac delta, there's a 2 pi that appears out of that too, and the 2 pi cancels the other 2 pi, and I guess, but I don't see why you get minus x. I don't know. Like I'm.
Oh, is that where the Dirac delta is evaluated?
I don't know. Like there's something here I don't understand. I'll just have to leave it at that at the moment. All right. Okay. Well, I think I've done just enough to be confusing. Let's see here. So the next section, section 512, we actually see how to solve some differential equations using the Fourier transform. So I guess I have to wait till next time to do those. I'm sorry, I was trying to get more done. But I think I have to go actually at the moment. I'm sorry, guys.
All good.
It's one of those days. So I will think about, let's plan for next Wednesday is test on chapters 3 and 4 in here.
Okay.
I'll probably make it a take home because I think we're out of time, you know? Is that okay? Or what do you guys, do you have the matter?
Just is it like a 24-hour deadline, you think?
Yeah, we could do something like that.